through and show you how we can actually use the concept of concentration and molarity actually as a conversion factor in our stoichiometry problem. So keep in mind the units for molarity are molar. So we represent that with the capital M. Now molar is simply a way of, the capital M actually represents moles over liters. So just like when we have grams per liter, we can actually use this as a conversion factor. So let me show that to you in this problem. So the question tells you how many grams of silver chromate will precipitate when 100 milliliters of 0.400 molar silver nitrate solution is added to potassium chromate. So before I do anything, I've got to write out my reaction. So it tells me I have silver nitrate reacting with potassium chromate. So silver nitrate, silver is Ag. It has a +1 charge. Nitrate is NO3, and it has a -1 charge. So I cross my charges properly here. Potassium chromate, potassium's +1. Chromate is CrO4 with a 2- charge, so you'd have a subscript 2 there. And so my products, since this is going to be a double replacement reaction, my products would be silver chromate, so Ag and CrO4, and potassium nitrate, K and NO3. So Ag has a +1 charge. Chromate has a -2 charge, so this would become Ag2CrO4. And then my other product is going to be potassium nitrate, so KNO3. So the last thing I've got to do really quickly is balance. I've got 2 potassiums here, so I'm going to put a 2 here. And then I've got 2 silvers here, so I'm going to put a 2 here, and I'm balanced. Now comes the stoichiometry part of it, now that I have a balanced reaction. So I am given, if I look at this problem, when I read it again, how many grams of silver chromate, that's what I'm solving for, will precipitate when 100 milliliters of 0.400 molar silver nitrate is added to the potassium chromate. So my given in this problem is actually the 100 milliliters. And I know that because I'm going to be using the molarity, the concentration, as my conversion factor. So I'm going to start off with 100.0 milliliters. Now, keep in mind, I just said I'm going to be using my concentration as a conversion factor. Well, to use this conversion factor, moles per liter, I've got to get my milliliters into liters first. So I'm going to divide by milliliters to get into milliliters and get into liters. Okay, so keep in mind 1 milliliter is 10 to the -3rd liter. So I am now in liters of my silver nitrate. Here is the only new step in this entire problem. It is this. I can actually go from liters, get out of liters by putting it on bottom so that they'll cancel, and I can get into moles of my silver nitrate of AgNO3. Now the way that I do that, if you look, moles per liter, that is my concentration, that's my molarity. So since I'm told that I have 0.400 molar of silver nitrate, I can just put that concentration here. So 0.400 moles for every 1 liter. So now that I've used that conversion, I'm now in moles of silver nitrate. This is now a typical stoichiometry problem because I can go from moles of silver nitrate, I can get out of moles of silver nitrate by putting it on bottom, and then I can get into what I'm interested in, which is grams of silver chromate. So I want to get first into moles of silver chromate, and then I'm going to do one last conversion, and I can get out of moles of silver chromate and into grams. So keep in mind, this was from the previous lesson. My mole to mole ratio, I just need to use my coefficients. So the coefficient in front of silver chromate is a 1, in front of silver nitrate is a 2. And then here, since it's grams per mole, remember I'm going to be using my molar mass as my conversion factor. And the molar mass, once I add up the molar mass of silver times 2 plus chromium plus oxygen times 4, I got 331.74. So that's grams for every 1 mole. All right, so now I need to take 100, multiply by 10 to the -3rd, multiply by 0.400, divide by 2, multiply by 331.74, and the final answer that I get for the grams, if I round to 3 significant figures, is 6.63 grams, and that is my final answer. All right, so notice the only new concept here is using your molarity as a way for you to get out of liters into moles. Or I could use it to get out of moles into liters, which we're about to do. Right? So these problems really don't get any harder than this. There are a lot of steps, so make sure that you're showing all of your units. So I'm going to erase this. We're going to go on to number 2. All right. So for number 2, you are told, let's see. All right. Number 2, zinc reacts with hydrochloric acid to produce hydrogen gas, which is H2, and ZnCl2. So I actually, at the top of this, I actually already gave you your entire reaction, and it's balanced. So that actually makes this easier than the previous problem. Okay? It says how many liters of a 1.50 molar HCl solution completely react with 5.32 grams of zinc. So keep in mind, I'm going to be using my concentration as a conversion factor. So my given here, what I start with, is 5.32 grams of zinc. Okay? And I'm eventually going to try and get into liters of HCl. Okay? So let's see how I do that. Well, I need to get into moles of HCl before I can even think about liters of HCl. So I'm going to first get into moles of zinc so that I can use my mole to mole ratio. Okay? So I need to put the molar mass of zinc. So the molar mass of zinc is 65.38 grams per mole. I'm now in moles of zinc. I want to get into moles of HCl, so I'm going to put moles of zinc on bottom and moles of HCl up top. Okay? The coefficient in front of HCl is a 2. The coefficient in front of zinc is a 1. So I'm now in moles of HCl. Normally, up until this point, we've converted into grams and we're done. But that's not what the question's asking for. It's asking you to get into liters. So I'm going to do that. I'm going to put moles of HCl on bottom and liters up top. Now, notice this is moles per liter, so I can use this concentration, the 1.50 molar of HCl, because remember, you can either write 1.50 molar or 1.50 moles per liter. So I'm going to put 1.50 moles on bottom because it's 1.50 moles for every 1 liter. Okay, so then all you've got to do is take 5.32 grams, divide by 65.38, multiply by 2, and divide by 1.50. Okay. Look at all of your values that you started with. I have 3 sig figs in 1.50 and 3 sig figs in 5.32, so my final answer should have 3 sig figs. So the answer that I got was 0.108 liters. And that was my final answer. Okay, let's try one last one. Example number 3. And then you guys will try it on your own. All right. In this problem, it asks how many milliliters of a 0.250 molar barium chloride solution are needed to react with 0.0325 liters of a 0.160 molar sodium sulfate solution. There are a lot of values here. I know the concentration of barium chloride. Let's get a pen that works. I know the concentration of that. I know the concentration of sodium sulfate, and I also know the volume of sodium sulfate. So what I'm going to be doing is converting. I need to go from the volume of sodium sulfate, because that's your given. Remember, we're going to be using concentration as a conversion factor. So I'm going to start with my volume of sodium sulfate. Okay. And I'm going to first get into moles of sodium sulfate. The way that I do that is I'm going to put liters on bottom and moles of sodium sulfate up top. Keep in mind moles per liter, that is molar, and I know the concentration of sodium sulfate, it's 0.160 moles for every 1 liter. So now that I'm in moles of sodium sulfate, I can get into moles of barium chloride, which I'm interested in, by just using my mole to mole ratio. So moles of sodium sulfate on bottom, moles of barium chloride up top. Let's look at my coefficients. Barium chloride, there's a 1 in front of that, and there's a 1 in front of sodium sulfate, so it's just 1 to 1. Now I'm in moles of barium chloride, but I want to be in milliliters of barium chloride. So I first need to get into liters. So I'm going to put moles of barium chloride on bottom and liters up top. Whenever you have moles per liter, you can use your concentration. So I know my concentration of barium chloride is 0.250 moles for every 1 liter. I'm going to do one last step. I'm kind of running out of space. I need one more step, however, because it asks for milliliters and I'm currently in liters. So I'm going to put liters on bottom, milliliters on top. 1 milliliter is 10 to the negative third liters. Okay? So at the very end, when I'm done with this, I'm going to take 0.0325, multiply by 0.160, divide by 0.250, and then divide by 10 to the negative third. And the answer I get, so that I can have 3 significant figures, since this has 3, 3, and 3, I end up getting 20.8 milliliters. So someone in one of my classes had expressed concern about these conversions here, especially with prefixes. So there are only really, for this class, there are only really 2 prefixes that I expect you to have memorized. And it's just because we use them in everyday life. The first one is kilo, right? So knowing that, for example, 1 kilogram is 10 to the third grams. I expect you to know that. You should know how many grams a kilogram is. And the other one is this milli, so that 1 milliliter is 10 to the negative third liters, or you could say 10 to the third, or 1,000 milliliters equals 1 liter. I expect you to know those, okay? So the kilo and the milli, so I wouldn't give you this conversion if I asked for that on a quiz or a test. All right, so just one more potential conversion factor that we're using when we're using molarity in a solution stoichiometry problem. Make sure that you're just comfortable with playing around with units, really. It's really just figuring out how do I go from one thing to the other using these conversion factors. So you'll have lots of practice in your notes and then also in your worksheet with this.